When a mass m is destroyed completely, the equivalent energy E is produced. Thus, according to Einstein's mass-energy equivalence equation, 1 kilogram of matter can produce a humongous amount of energy, which is E is equal to 1 into 3 into 10 raised to 8 square joules, equal to 9 into 10 raised to 16 joules of energy. The energy produced by 1 kilogram of mass is equivalent to the annual electrical energy produced by a power generating station, that is 3000 megawatts. Now, if 1 gram of mass is completely destroyed, the energy produced is expressed as E is equal to mc square, that is equal to 0.001 into 9 into 10 to the power of 16. That is equal to 9 into 10 to the power of 13 joules. One of the most expensive forms of energy is nuclear energy. Nuclear energy is energy derived from a nuclear reaction, such as nuclear fusion or nuclear fission, from which energy may be released in accordance with Einstein's mass-energy equivalence relation. In nuclear fission, a heavy nucleus like uranium-235 absorbs a slow neutron and hence splits into lighter nuclei. The final mass of products is observed to be less than the total mass of the reactants, and this difference in mass is known as mass defect, denoted by delta M. The mass defect delta M is converted into energy in accordance with E equal to delta M into c square. In a nuclear fusion reaction, lighter nuclei fuse to form a heavier nucleus. This fusion is accompanied by the release of a large amount of inherent energy in accordance with the mass-energy equivalence relation. In nuclear fusion too, there is a mass defect which accounts for the amount of energy released according to E is equal to delta M into c square. The source of the massive amount of energy released by the Sun and the stars is believed to be due to a nuclear fusion reaction, when isotopes of hydrogen, namely deuterium and tritium, undergo fusion to form an isotope of helium and a neutron with the release of a large amount of energy. The energy released is due to the conversion of a mass defect between the reactants and products in the reaction. The law of conservation of energy states that the total energy of an isolated system is always conserved and that energy can only be transformed from one form to another, but can neither be created nor destroyed. For example, when a firecracker explodes, the chemical energy stored in it is converted into light, heat, and sound energy. Nuclear energy is used to produce electrical energy in a nuclear reactor. Different forms of energy are used to do work. Earlier, we learned that work is said to be done when a force F acting on a body displaces the body through D in the direction of the force. When work is done, energy is transferred. The rate at which work is done or energy is transferred is called power. Thus, power P is equal to work done W by time T. Instantaneous power P is equal to dW by dt. But dW is equal to F dot dr, where dr is the displacement. Therefore, P is equal to F dot dr by dt, which is equal to F dot V. Since dr by dt is equal to instantaneous velocity V. Power is a scalar quantity and its SI unit is watt, and its dimensional formula is m power 1, L power 2, T power minus 3. Power can be expressed in horsepower denoted as HP, and 1 horsepower is equal to 746 watts. The commercial unit of electrical energy is kilowatt hour denoted as kWh. 1 kilowatt hour is equal to 1000 watt into 1 hour, and which is equal to 1000 watt into 3600 seconds, and is equal to 36 into 10 to the power 5 joules. We come across many types of collisions between different bodies in our daily lives, like the collision between a bat and ball, and the collision between a striker and coins in a game of carom. In the subatomic world, we find collisions between various subatomic particles. For example, a subatomic particle called a neutrino collides with another subatomic particle, a neutron. The neutron disappears and one finds a proton and an electron as products of this collision. In any collision, the linear momentum of the system is conserved. If we consider one-dimensional collision between two bodies, then from Newton's third law of motion, they experience equal and opposite forces, F12 and F21, on each other, such that F12 is the force on the first body due to the second, and F21 is the force on the second body due to the first, and F12 must be equal to minus F21. From Newton's second law of motion, if delta P1 and delta P2 are changes in momenta of the first and second bodies respectively, then force F12 will be equal to delta P1 by delta T, and force F21 will be equal to delta P2 by delta T. Since F12 is equal to minus F21, this implies that delta P1 by delta T is equal to minus delta P2 by delta T. Therefore, delta P1 is equal to minus delta P2, or delta P1 plus delta P2 is equal to 0. Hence, we can say that the total change in momentum during a collision is 0, or we can say that the total momentum of the system is conserved during collisions. There are 3 different kinds of collisions: elastic collision, inelastic collision, and completely inelastic collision. In a collision, if both the total momentum P and total kinetic energy Ke of the colliding bodies is conserved, then it is an elastic collision. In such a collision, the bodies move separately after the collision and the loss in kinetic energy delta Ke is 0. This implies that there is no loss in kinetic energy. For example, the collision between subatomic particles is an elastic collision. In a collision, if only the total momentum of the colliding bodies is conserved and not the kinetic energy, and the colliding bodies move separately after the collision, then the collision is called an inelastic collision. There is some loss in kinetic energy of the system during this collision. This implies that delta Ke is not equal to 0. For example, the collision between billiard balls is an inelastic collision. In a collision, if only the total momentum of the colliding bodies is conserved and the total kinetic energy is not conserved, and the bodies stick together after the collision, then it is a perfectly inelastic collision. There is a maximum loss of kinetic energy during this collision. This implies that delta Ke is maximum. For example, the collision between a clay ball and a metallic ball is a perfectly inelastic collision. Consider a head-on collision. That is, one in which the velocities of the bodies before and after the collision are along the same straight line. The mass of the first body is m1 and is moving towards right with velocity u1. The mass of the second body is m2 and is also moving towards the right with velocity u2, such that the two bodies are moving along the same straight line. If u1 is greater than u2, then there will be a collision between the two bodies. Let the collision between the two bodies be elastic, which implies that it is a completely elastic collision. Let the velocity of m1 be v1 and that of m2 be v2, just after the elastic collision. Since the momentum is conserved, we have m1u1 plus m2u2 is equal to m1v1 plus m2v2. On rearranging the terms and simplifying, we get m1 into u1 minus v1 is equal to m2 into v2 minus u2. Let this be equation 1. Since the total kinetic energy is also conserved in an elastic collision, we have half m1u1 square plus half m2u2 square is equal to half m1v1 square plus half m2v2 square, or m1u1 square plus m2u2 square is equal to m1v1 square plus m2v2 square. On rearranging the terms and simplifying, we get m1 into u1 square minus v1 square is equal to m2 into v2 square minus u2 square. On further simplifying, we get m1 into u1 minus v1 into u1 plus v1 equal to m2 into v2 minus u2 into u2 plus v2. Let this be equation 2. Now, dividing equation 2 by equation 1 and simplifying. We get u1 plus v1 minus u2 is equal to v2. Let this be equation 3. Substituting value of V2 from equation 3 in equation 1 and simplifying as shown. We get final velocity of m1 as v1 is equal to m1 minus m2 by m1 plus m2 into u1 plus 2m2 by m1 plus m2 into u2. Let this be equation 4. From equation 3, we get v1 is equal to v2 plus u2 minus u1. Let this be equation 5. Substituting the value of v1 from equation 5 in equation 1 and simplifying as shown, we get final velocity of m2 as v2 is equal to m2 minus m1 by m2 plus m1 into u2 plus 2m1 by m2 plus m1 into u1. Let this be equation 6. As a special case, if we assume that m2 was at rest before the collision, then u2 will be 0 and v1 reduces to v1 is equal to m1 minus m2 by m1 plus m2 into u1. Let this be equation 7. And v2 is equal to 2m1 by m2 plus m1 into u1. Let this be equation 8. Moreover, in this case, if m1 is equal to m2, say equal to m, then we get v1 is equal to 0 and also v2 equal to u1. Thus, we see that the two bodies exchange their velocities after the collision. If m1 is much greater than m2, then we neglect m2 in equations 7 and 8. Thus, we get v1 from equation 7 equal to u1. And also, we obtain v2 from equation 8 equal to 2u1. Therefore, in such a case, we see that m1 continues to move with the same velocity as it had before the collision. Whereas, m2 now acquired double the initial velocity of that of m1. In a real-life situation, we do not encounter collisions where bodies before and after colliding move along the same straight path. They collide in two dimensions, as usually observed in a game of billiards or carom. Consider an elastic collision in two dimensions, where a body of mass m1 with velocity u1 along the x-axis collides elastically with a body of mass m2 at rest. This implies that the velocity of m2 before collision, u2, is 0. Just after the collision, m1 moves away with velocity v1, making a positive angle alpha with the x-axis, and m2 moves away with velocity v2, making a negative angle beta with the x-axis. Since the collision is elastic, the total momentum and total kinetic energy of the system must be conserved for the bodies. The law of conservation of momentum must be applied both along the x-axis as well as the y-axis. v1 cos alpha and v2 cos beta are the components of v1 and v2 respectively along the x-axis. Hence, according to the law of conservation of momentum applied along the x-axis, we get m1u1 plus m2u2 is equal to m1v1 cos alpha plus m2v2 cos beta. And on simplifying, we get m1u1 is equal to m1v1 cos alpha plus m2v2 cos beta. Let this be equation 9. v1 sin alpha and minus v2 sin beta are the components of v1 and v2 along the positive y-axis and the negative y-axis respectively. Hence, according to the law of conservation of momentum applied along the y-axis, we get m1u1 plus m2u2 is equal to m1v1 sin alpha minus m2v2 sin beta. As the initial velocities of the two bodies along the y-axis are 0, we get 0 on the left side of the equation. And thus, we get 0 is equal to m1v1 sin alpha minus m2v2 sin beta. On further simplification, we get m2v2 sin beta is equal to m1v1 sin alpha. Let this be equation 10. Since the total kinetic energy is also conserved in an elastic collision, and as u2 is 0, we have half m1u1 square is equal to half m1v1 square plus half m2v2 square. On simplifying, we get m1 into u1 minus v1 into u1 plus v1 is equal to m2v2 square. Let this be equation 11. The total quantities among the three equations are m1, m2, u1, alpha, beta, v1 and v2. Thus, there are 7 quantities and 3 equations. By knowing the values of m1, m2, u1 and at least one among alpha or beta, we can determine the values of V1 and V2. Now, consider a head-on collision, that is, one in which the velocities of the bodies before and after the collision are along the same straight line. That is, a one-dimensional collision. A body of mass m1 moving with velocity u1 collides with another body of mass m2 moving with velocity u2 in the same direction along the same straight line. Let the collision between m1 and m2 be completely inelastic. As the collision is completely inelastic, they stick together after the collision and move with a common velocity v. Since the momentum of the system is conserved during the collision, we have m1u1 plus m2u2 is equal to m1 plus m2 into v. This implies that the velocity after the collision v is equal to m1u1 plus m2u2 divided by m1 plus m2. Let this be equation 12. The loss in kinetic energy of the system, delta Ke, is equal to the kinetic energy before the collision minus the kinetic energy after the collision, which is half m1u1 square plus half m2u2 square minus half into m1 plus m2 into v square. We substitute the expression for the common velocity v from equation 12 in the expression for delta Ke and simplify as shown. For convenience, we mark two expressions, A and B, and simplify them separately as shown. Thus, the loss in kinetic energy in a completely inelastic collision is as shown on further simplification. As